In May 1943, somewhere in the cold North Atlantic, a German U-boat captain hears a sound he has never been trained to fear, a drawn-out mechanical whine that seems to follow his every evasive turn. Within minutes, his boat is crumpling from the inside out. Compartments flood, electrical systems fail, and the hull implodes far below safe depth. The crew has no torpedo hit to blame, no depth charge pattern to curse, only one terrifying conclusion. The hunter has become the hunted. Allied engineers call it the culmination of years of desperate work. The Kriegsmarine calls it impossible. But to understand how a handful of engineers and a new class of weapons rewrote the rules of undersea war, we need to go back to the winter of 1942 and trace a chain of innovations from listening devices and forward-firing mortars to a thinking torpedo called Fido. The year is 1942 and the Atlantic is bleeding. Merchant ships, tankers full of fuel, freighters heavy with food and munitions, are vanishing beneath U-boat wolf packs. At peak months, hundreds of thousands of tons of Allied shipping sink. Convoys are running a gauntlet. Intelligence has a crucial advantage. Enigma decrypts give Allied admirals a map of wolfpack intentions. But knowledge alone can't put an explosive in a steel tube cruising three-dimensionally beneath the waves. Detection and destruction are different problems. Surface ships can search, patrol aircraft can sweep, but the ocean is an acoustically hostile three-dimensional chessboard. Thermoclines bend sound, sea state and propeller noise mass targets, and diesel-electric submarines can dive deep and run silent. The Allied task sounds simple on paper. Find the sub, kill the sub, but in practice it is close to impossible. This is the engineering problem. Detect a relatively small, heavily built object, a pressure hull, moving under hundreds of meters of water, discriminate it from ocean noise, calculate range and bearing quickly, and deliver a weapon that will actually destroy the hull. Traditional approaches, passive hydrophones to hear propeller noise, depth charges rolled off the stern set to explode at a guessed depth, are blunt. They require the attacker to be in the right place at the right time, and to hope that the charge detonates within lethal distance. The Germans exploit that uncertainty. They train crews to dive deep, go quiet, and exploit ocean layers to slip into shadow zones. Allied engineers need a system that reduces uncertainty, better sensing, better weapons, and critically our integration between the two so detection immediately creates a lethal solution. Think of the ocean as a fogged hall where you must find a whisper and then throw a dart with surgical precision while both you and the whisperer are moving. That metaphor captures the constraints. Sound travels in water, yes, but it refracts through thermoclines. Echoes smear. Reverberation from the attacking ship confuses returns, and a submarine that hears a ping can duck into a shadow zone. The Allied answer is not a single magic piece of hardware, but a series of engineered advances that, when linked, create a new capability. Active and passive acoustic sensing paired to new weapon geometries and guidance logic. Two parallel threads matter most: improved detection and precision-delivered weapons. Together they transform hunting into killing. The first thread, detection, moves from crude hydrophones to integrated active-passive sonar systems and better signal processing. Laboratories and naval research groups, the U.S. Naval Research Laboratory, hunters at the Harvard Underwater Sound Laboratory, and industrial partners, push the science of underwater acoustics. How to shape pulses, how to cancel ship self-noise, how to process weak echoes and extract bearing and range reliably under real sea conditions. The second thread, weapons, moves from patterns of depth charges to forward-firing mortars like Hedgehog, and, most disruptively, to small acoustic homing torpedoes that can seek out a submarine's noise signature or home on an active ping return. The key conceptual leap is this. Instead of hoping a dumb explosive falls near a sub, build a weapon that can track and pursue the sub itself. There is no single instant of magic. There is an engineering breakthrough built from many smaller insights. One core insight is active sonar. Emit a controlled acoustic pulse, listen for the echo, measure time of flight and bearing, and thus obtain range and direction. But active sonar is a double-edged sword. The ping reveals the searcher's position to the target. Allied engineers answer by integrating active detection into a broader, faster kill chain. Quick pings, immediate fire control, and forward-fired weapons that strike before the submarine has time to react. Hedgehog mortars are part of this story. They project multiple small contact-detonated bombs ahead of the ship so that the attacker can keep sonar contact while delivering the explosive pattern. Hedgehog addresses a tactical problem: deliver explosives ahead of the ship, not astern while preserving sonar contact, but it still relies on statistically getting close enough for a contact detonation. The other major leap is the Mark 24 acoustic homing torpedo, the weapon that would come to be known by the affectionate nickname Fido. Where depth charges and Hedgehogs are area weapons, Fido is a seeker. It is designed to be dropped from aircraft into the water, survive the initial impact and deployment sequence, then listen. Using passive acoustic sensors, and in some modes limited active terminal guidance, it homes on the characteristic noises of a submarine, propeller cavitation, machinery hum, flow noises, and pursues the source. The engineering challenges are immense. Design sensors and signal processing circuits rugged enough to survive launch. Develop guidance logic that discriminates submarine acoustic signatures from ocean noise and from decoys. Power the electronics in a compact, reliable package, and package a warhead adequate to cripple a pressure hull while fitting into an airdrop torpedo form factor. Engineers solve these problems through clever mechanical and electronic design. They hermetically seal vacuum tube electronics, use pressure-compensated housings, develop impact decelerators and deployment mechanisms that slow the torpedo from aerial release speed to safe underwater entry, and implement analog signal filtering circuits that can identify the narrowband signatures of submarine machinery. They program search patterns into the torpedo's guidance, spirals expanding circles, so that if the target noise is lost, the weapon executes a methodical reacquisition. Importantly, designers keep the weapon small and agile. The goal is to explode close to the pressure hull and let the water's incompressibility and pressure wave do the damage. In water, a 100-pound warhead detonating within a few meters can be as lethal as a much larger hemispherical hit on a surface ship. Testing is brutal. Lab trials in calm harbors are one thing. North Atlantic weather and the agile maneuvers of trained U-boat crews are another. Engineers iterate constantly, tune sensor frequency bands, modify acoustic filters to reject bubble noise and release signatures, harden components for saltwater corrosion, and refine search algorithms. Meanwhile, naval aviators and escort groups practice release techniques, target tracking, and coordinated attacks so that detection immediately leads to weapon delivery. The breakthrough moment in the operational sense is not a single flash, but a sequence when Allied crews begin to see remarkably consistent results in combat. Aircraft release acoustic homing torpedoes. The torpedoes home on the submarine. The sub implodes or is fatally crippled in minutes. Past failures and long chases stop mattering. A paired innovation, forward-firing Hedgehog mortars linked to active sonar, amplifies the effect, giving surface groups a means to prosecute contact while maintaining sensor fidelity. Together, these two capabilities, the sense of a refined sonar chain and the effect of a homing weapon, create a systemic change in anti-submarine warfare. That change is visible in the first sustained combat results. Patrol aircraft begin reporting that acoustic homing torpedoes, when properly deployed against shallow to moderate depth targets, often yield swift results. The weapon makes contact, detonates, and the submarine is either destroyed or so badly damaged it must surface and is finished by conventional means. Escort groups using sonar, Hedgehog salvos, and coordinated tactics develop a rhythm. Find, fix, and strike. Repeat. U-boat captains who once relied on depth and silence for survival start to see their options vanish. They can no longer assume that diving deeper or going quiet will preserve them. A homing weapon can locate and chase the acoustic signature, and a forward-fired pattern can close the geometry so that escape is near impossible. Enemy reaction is predictable but constrained. German engineers scrambled to counter with acoustic decoys and new torpedo designs. They produced their own acoustic homing weapon, but industrial constraints, Allied strategic bombing, and a knowledge gap slow effective mass production and refinement. Countermeasures, bubble decoys that attempt to mask the submarine's acoustic signature or noise-making devices, work sometimes, but Allied designers anticipate and adapt. Signal processing that looks for the complex harmonic structure of a ship's noise rejects simple bubble clouds. Tactics evolve. Aircraft coordinate with escorts so that a torpedo's active ping is followed immediately by a Hedgehog attack. In effect, the Allies create an operational doctrine that leverages engineering superiority. Sensors, weapons, tactics and training fused into a single doctrine of hunter-killer warfare. The strategic impact is profound. Where once U-boats could dominate convoy lanes with near impunity, by mid-1943, losses of U-boats begin to mount. The attrition of trained U-boat crews and the loss of experienced commanders degrade the Kriegsmarine's effectiveness. The Atlantic's terror economy, where a single U-boat patrol could sink dozens of thousands of tons of shipping, is broken not by bigger guns but by better sensors and smarter weapons. Supply lines stabilize. Convoys reach port. Amphibious campaigns gain the logistical certainty they need. Put bluntly, engineering reduces uncertainty in the 3D battlefield, and the geopolitical consequences flow from that reduction. The legacy of these innovations is visible in the Cold War and the modern era. Acoustic homing concepts evolved into more capable torpedoes and into the complex towed arrays and distributed sonobuoy networks that navies use today. Signal processing techniques pioneered under wartime constraints matured into digital filters and adaptive algorithms. The same mathematical ideas that separate signal from noise underwater later underpin sonar, radar, and even civilian applications like medical ultrasound and noise cancellation. Hedgehog's concept, forward engagement while maintaining sensor contact, echoes in modern weapon placement and unmanned system tactics. In short, the marriage of sensing and effectors that engineers welded together in 1943 becomes the blueprint for future sensor-to-shooter paradigms. All of this raises an engineering lesson. Battlefield innovation often emerges from integration rather than isolated breakthroughs. A brilliant sensor is only as valuable as the weapons and tactics it enables. A powerful weapon is only as useful as the sensor that finds the target. The Atlantic campaign shows the multiplier effect when detection, guidance, and ordnance are designed to operate as a system under real combat constraints. The result is not just tactical success but strategic leverage. If you imagine the ocean again as a fogged hall, the Allied solution is no longer to shout and hope. It is to listen with instruments that filter out the orchestra, to send agile seekers into the fog that home on the faintest whisper, and to coordinate teams so the seeker finds and the team finishes the job. That chain, listen target, prosecute, explains how a handful of engineers, many working at naval labs, university sound labs, and industrial partners, could produce weapons that German engineers described as violating expectations of the physics. In truth, the engineers had done what engineers always do. They asked better questions. They found smarter ways to measure the world, and they built rugged, practical systems to act on those measurements. Before we go, a few production notes for editors and visuals that will elevate this story on screen. Show black and white archival footage of convoy and U-boat periscope. Animation. Cross-section of a U-boat showing pressure hull, ballast tanks, and depth markings. Show diagrams of active sonar ping and echo timing. Close-up replica Mark 24 Fido torpedo with exploded view of guidance sensors. Animation spiral search pattern of homing torpedo. COP Atlantic convoy routes with hunter-killer group patrol areas highlighted. Archival footage, Catalina flying boat and escort carrier deck operations. Animation, shockwave propagation and water and pressure effects on hulls. Sprinkle these throughout the script to give viewers visual anchors every 20-30 seconds and maintain retention. If you enjoyed this deep dive into how engineering changed naval warfare, hit subscribe. We're building a series on battlefield engineering that connects historical innovations to modern tech. Drop a comment. Which piece of the chain surprised you most? The sensing, the weapon design, or the tactics that tied them together? And if you want this made even tighter for voiceover timing, I'll produce a shot-by-shot edit deck and a 12-minute narration track ready for production. Thanks for watching. Remember, in war and in peace, the side that hears better and acts faster usually wins.